good afternoon or hello. So I'm gonna talk a little bit because I'm coming from the National Institute of Standards and Technology. We're gonna talk about communications measurements and modeling. Next slide, please. So for those of you who don't know what NIST is, we're part of the U.S. Department of Commerce. We are composed of 6 laboratories and ranging from material measurement to neutron research. And I'm coming from the Communications Technology Laboratory that we focus on sort of connectivity, performance, in support of growing the economy and improving lives, tall order. Anyway, so next slide, please. Just I don't believe I need to do a lot of context setting here in Vision. I was preceded by very distinguished speakers, and I'm sure there'll be other distinguished speakers following me. So you guys are pretty much set in terms of Vision. I will bring up a few needs and measurement challenges in the context of Spectrum innovation. And I will talk to you a little bit about our programs at NIST that address some of these measurement challenges and needs, and then also bring up some collaborations going forward. Next slide, please. So again, needless to say that, the vision for the beyond 5G, the next G, the 6G is basically a huge amount of data, very low latency. Things will happen very quickly. Machines will respond to machines, to humans, and that would, it requires a very huge amounts of data and very low latency, right? I mean, right now we're interfacing with the Zoom, wouldn't it be nice if we can see some holographic, kind of interactions, making this interaction a little bit less robotic and a little bit more personal. So maybe 6G, maybe the next G. Next, please. So for those of you who haven't seen the infamous 5G pyramid, I just wanted to flash it back to you here just to remind you that this is where we were just a few years back and where we're heading. In terms of again, using the data, using the very robust 5G and next G infrastructure, and the use of machine learning and AI, so that we really are looking at enhanced automation, enhanced control, but also most importantly, enhanced intelligence, even in the communication infrastructure. Next slide, please. So in this context, right, we have for future and current spectrum needs, we're looking at also all the spectrum regimes, and we're going to use all of them from licensed to unlicensed, and sharing different models, hierarchical, distributed, centralized, decentralized. And what's clear is that we really need large spectrum swath to support, wider channel bandwidth. Whatever it is today, we need it wider. We need dynamic allocation and high frequency reusability so that we are always doing the best we can to utilize more efficiently the spectrum. But also we need to look at the future and look at the higher bands, millimeter wave, terahertz, and beyond. And I believe Ted will have a very excellent report on his measurements in that band. Next slide, please. So the measurement challenges that sort of like are in front of us today, and I believe in the future, will be, and this is by no means an exhaustive list, right? So the key challenges in measurement has been sort of looking at how do we characterize aggregate interference. Like, it's not so much just one receiver on one interfere on a victim. It's basically when you have a lot of potentially interferes, and how do you characterize, how do you come up with a good handle on aggregate interference? It's also because we're dealing with communication devices, but also non-communication devices, including these, passive sensors, for example, in weather satellites or other devices. So how do we, characterize interference when you have this fundamental heterogeneity in the devices that are going to be out there? Obviously, propagation. Again, we've done a lot in propagation over the years, and I believe there's still more work to be done in propagation measurement in order to really understand, the characteristics of the signal as it travels. How do we characterize all the various effects? So we're still, some people say we have scratched only the surface. Some people are say more confident, but regardless, I think we still have a lot to learn from there. Next slide, please. So when we talk about measurements, obviously the next part is about models, right? It's about developing abstractions from measurements, typically, right? For measurements are we want to qualify, characterize a scenario. We want to generalize the scenario so that we look for these models, right? Abstracted from measurements. We have to also think about nowadays machine learning, right? We've been bombarded with machine learning this, machine learning that. Obviously, we in signal processing and wireless communications have been using machine learning for decades, right? And mostly in the descriptive sense, in the predictive sense. This is what channel propagation, how we come up with channel propagation models. But it's mostly used offline when we analyze large data sets, right? So how do we go from this descriptive, predictive regime to a more prescriptive model where we can act on insight, where things become more dynamic. So far we have no simple solutions, right? We're throwing lots of data at the problem, processing power, and we're using decade-old machine learning algorithms. Obviously, we think that in order to do a good job with this, you have to have key, domain expertise, right? So data scientists alone can't just come up with good models, but still, it's mostly about, lots of data and processing power and what people have been using. Next slide, please. So where to apply machine learning? So communication, lots of problems and functions in communications, we can apply machine learning. And again, we're talking about the decade-old algorithms applied to problems from signal detection to antenna configuration to MIMO optimization to end-to-end performance and quality of experience and quality of service to planning and coverage, right? Wherever you have, optimization problems with over large sets of variables, whenever you're trying to approximate, functions that are extremely computationally expensive, so this is where you apply machine learning. And some people now are looking at, adapting these machine learning algorithms to the communication infrastructure, to the asymmetry, in the infrastructure, right? Edge computing, you have the federated so-called learning, the distributed learning, right? That is, sort of what's happening, and that is important. I want to pose another interesting aspect to this, is that, instead of just, designing, the next greatest and latest in communications infrastructure, applying the old machine learning, trying to adapt those, what if we also look at it from designing communications infrastructure to support this machine learning or this AI-centric vision of communications, right? So shouldn't we also look at it from the other aspect, as in, how do we adapt the infrastructure? How do we design new infrastructures? Is a bit any bit is the same, whether we're carrying data for voice traffic or for video or for AI applications, right? Maybe there should be other communications and protocols that we need to adjust, whether depending on what we're trying to do, right? And maybe we need to design both comms and machine learning uh, in more of a co-design conjunction combination, so that we can come up with really truly intelligent communications, right? As opposed to just applying, using communications as another way to apply machine learning. And I believe we probably, as a community, we probably need to think along those lines, because we're competing. When we say, oh, we're also using AI, they say, hey, okay, join the club, line up, because there's so many applications for AI and machine learning, right? We're just one of so many different communities using that. But really, I think what our job is, there's no machine learning and AI if there's no comms to support it. So how do we really focus on new designs for new comms to support, you know, intelligent communications? So that's my my new, I think, thinking in terms of, you know, where we need to go forward and further. Next slide, please. Okay, machine learning, great, that's awesome. We can apply it. We saw to different functions and different optimization problems. Then comes the uh, more difficult problem is where are the wireless data sets, right? For folks in the operators, you know, telecom operators, ISP providers, the Googles, the Facebooks, people with data, they could do it, right? They've been doing it, in fact, for a decade or more. At least that's what I'm told. But for the rest of the folks in the research community, those folks that we rely on them for the next innovative algorithms and the next designs and architecture of the communication systems, where would they get their handle on these wireless data sets? How would they, where would they go to get these data sets? So there is a need to have, you know, these data sets similar to what exists in other domains, in speech, in handwriting, in object recognition. And so far, we are very far away from that. Next slide, please. So what we need is, again, is publicly available databases with RF signal communication data. We need to look at the different data sets, right? Not everything is going to be RF. Some is going to be RF. Some is going to be more traffic mobility. Some is going to be packet. Some is going to be interlayer, right, of traceable data. We need to look at from the channel, the signal, to noise, to network scenarios, so different environments and configurations. These can come from field measurements, you know, live networks is even great, test beds, simulation, right? The people who are running networks have this data again, but they are not willing to share it. They cite privacy, security concerns. You know, it's not easy to say, here's my data set, right? But for the test beds, the community can start collecting these test beds. I mean, it's great to have test beds in the community where we can do something like that. However, so far it's not organized, right? The first person who runs the experiment gets this awesome data, awesome result, publishes a paper, and the students, you know, graduate. And then what comes the next generation of students that have to do the same thing? But they have to do this same thing in order to go further. They'll have to just, you know, sort of redo some of that what was done before. So there is really a need to, you know, in terms of making this available so that everybody can start with something that they could use to move forward. And again, it could come from field measurements, it could come from test beds. There's some available in the community, NSF, with the community made available. I believe Cosmos is run by some of the teams on this part of this team as well. And from if you don't have access to any of this, simulation is okay too. And it's not one is better than the other. I think you probably need all of these in order to obtain these data sets. Next slide, please. So now I want to tell you a little bit about our programs at NIST in relation to what I just talked about. So our efforts, you know, span the 5G and beyond scope. We're looking at domain specific, you know, with public safety research, advanced manufacturing. We're looking at Spectrum for testing Spectrum. We're looking also at security in the bottom. How do we secure the infrastructure? And also, we also look at advances in communications metrology. And this is the part I'm going to focus on today with respect to measurement and modeling. Next slide, please. So if I want to, you know, describe again the measurements, the modeling needs for this enhanced intelligence and discuss, you know, the measurements, models, machine learning, and communication data sets. You know, all of these ingredients, I believe, or or thrusts that are kind of important to think about, especially in the context of a Spectrum Innovation Center. Next slide, please. So we have a large program in millimeter wave measurement and modeling. This is, a decade now old, starting with first generation sounders. Now we're at our third generation sounders that are based on phased arrays for different frequency bands. We have modeling capabilities, and again, not just to create a single model, right, but to create, a variety of models and support different, modeling of different features of the wireless signal. And next slide, please. And we've spent a few years now working very closely with several tool vendors, RF tool vendors, trying to augment or enhance their capabilities in terms of modeling capabilities with the measurement-based data that we have, right? So we work very closely with folks like MathWorks, ANSYS, Cyrodiil, Remcom, and others to really help them to put the measurements that we have and enhance the models they have. So this is often a tedious process. We have our measurements, it's available. I'll explain where and people can get that, but it's often not easy to take the measurements and run or read the paper and understand exactly what to do. So we often had to work very closely with folks in order to say, hey, here's how you can use this. So it's a very, it's a two-way conversation that sometimes spans over several months, but then leads to, publications and lead to models that they can use in their libraries and their products. Next slide, please. Another aspect that we're looking at here is the AI-aided channel modeling. Of course, we've been using machine learning to develop channel models from measurements, but because we have so much data in terms of measurement data, our sounders, are pretty awesome in the sense that they can produce tons of data just in the span of a few hours, right? The bottleneck for us is about processing the data and developing the models. So we're using AI to really help us to automate the process, but also speed it up, so that we're using cameras on top of the sounders in order to get the image, the videos of the environment as we're scanning the environment. And then we use the video and the AI in order to classify the objects in the environments and then map that, the multipath components to those different objects and classes. So that is helping us quite a bit. We've started using this fairly recently, the last year or so. Next slide, please. Another aspect in modeling and measurement is these tools, right? When you need to evaluate different algorithms, different approaches, different mechanisms, you're really looking at going from measurements to abstracting models, but also to using these measurements into tools that are accurate. And we've spent a little bit of time in the last 3 years developing this, going from measurements for 60 gigahertz all the way to including that into simulation tools like NS3. This is for the 11AY suite. I believe at NYU, they've done similar for 3GPP and for new radio. But this is sort of the exercise is taking something from measurements all the way to putting it into tools and platforms that people can use. And again, this is available for the community to use on GitHub. Next slide, please. So again, use of AI, there's no shortage of using AI and machine learning for the different approaches. And here we're using AI-aided beamforming and training. We've recently participated in the ITU challenge that was posted last fall, looking at data and using AI in order to come up with beamforming and training. So that's another promising area for also looking at combining data, LiDAR, measurement data in LiDAR and making some optimization. Next slide, please. Now I'm going to talk about collaborations, right? A lot of these programs that we have are tied to efforts we have working together with the standard developing organizations on one hand, with industry, with the research community. And so some of it is in the context of SDOs like 3GPP, like IEEE 802, like the Wireless Innovation Spectrum Forum, WIN Forum, and TIP. And others are in terms of more of partnerships with other government entities and also with industry and academia. So and another kind of coordination function we have at NIST is the so-called NASTN, which is a National Advanced Spectrum Coordination Test Network, which is sort of a coordination across different agencies that work together in order to facilitate access to laboratories testing for spectrum. So that's something to keep in mind. Next slide, please. So I want to talk a little bit about the 5G millimeter wave channel model alliance. I think some of you are aware of it, are part of it. Basically, launched in 2015. To date, we have over 80 organizations. We have a robust participation. We even have, next slide, please. We have over 80 data sets of propagation measurement from 8 organizations around the world, including NIST. So people can access this data and use it. We also, so not all producers are also, not all consumers are also producers. So there's some going to be just users of the data. Some are going to be just developing models of the data. Some are going to be just developing measurement data. So the idea here is that there is a little bit of curation here that goes that where we're looking at data sets, we explain templates, how things should be organized, what is, in order to reuse the data, one has to make sure that it is accurately described, the scenarios are described, and then all the material, supporting material is available. So this is another resource to keep in mind. Next slide, please. And then another also, in terms of data sets, this is more on the radar waveform data sets, which is following an experiment to collect radar data, radar signals in the CBRS band. And because we were not able to share the data, the waveforms that was collected due to the DoD approval, we were able to synthesize the data or use the data to analyze it and then come up with synthetic or emulated data set. And then we have tools that actually could help people to play a little bit with the data so that they can run their detection algorithm again. So this is another example of making data sets available to the community. I believe this was my last slide, and I hope I'll have time for a couple of questions. Thank you.